present the project Micro PPI Lascombes Polytechnique thruster for Cubesats. It's a project led by the Ecole Polytechnique and the University of Versailles-Saint-Quentin, and we created a structure to get extra funds. It's called Exotrail, and that will develop further the thruster. So the summary of my presentation is first I will talk about what is space debris, what are the consequences of space debris, then our propulsion unit, so what we are doing now, and finally what are the services and what we have to develop to add to the hardware of the propulsion unit in order to have an effective propulsion system. So first about space debris, so we have an exponential increase of space debris linked to the number of satellites in space, because when you have a lot of satellites in space and that one is destroyed by a debris, it creates thousands of other debris. So you have an exponential increase, and you have a very slow natural decay of those debris. So below 500 kilometers, the debris are re-enter in less than 30 years, but when you go to 800 kilometers, it takes centuries to re-enter. So if we pollute the space now, we will never be able to clean it for future generation. And those debris can be very dangerous because the relative speed of one debris relative to a satellite can be as high as 15 kilometers per second. And what is interesting is that in the recent years, the flux of man-made space debris is higher than the flux of natural objects such as micrometeorites. So basically, we have more than doubled the risk to get to have a satellite being destroyed by debris. And those debris are very complicated to track. So we can track 1 centimeter debris in LEO and 10 centimeter in GEO. When you know that one debris of 1 centimeter can go through 5 centimeter of aluminium. Therefore, nothing can withstand an impact of even 1 centimeter debris. Then, consequences of those debris. So, the main concern is an economic rationale, because if you have too many debris in space, you cannot launch safely your spacecraft anymore. And you have overloaded orbits, such as the sun-synchronous orbit for LEO and the geostationary orbits. Therefore, it will lead to a loss of business opportunities, because if you cannot use those overloaded orbits anymore, you cannot make sun-synchronous imagery, for example. And it will be an impossibility to launch large constellations, because they are all at the same altitude, and you have too many debris at one altitude. You won't be able to deploy constellation of hundreds or even thousands of satellites, such as what OneWeb or SpaceX are planning. It also has strategic consequences, because it might lead to a loss of global imagery system, which is necessary nowadays for intelligence agencies, and you have an additional risk when you want to launch satellites at a higher altitude, because the launcher should not be harmed by the environment. And what can we do to mitigate the risk? The first step is at an institutional level. So we have directives and laws that say that satellites should deorbit in less than 25 years after the end of the mission, and it's mandatory if you're not from the US, from France. And you also have a lot of projects that are funded by space agency to study deorbitation. And for satellite owner, they have to ensure that they can have enough fuel reserves in order to deorbit their satellites. And another additional feature to avoid the creation of new debris is to use LGO spacecraft that can make avoidance maneuvers in order not to be hit by a debris. That's why there is a need for an efficient thrusting device for our satellites in order to deorbit them if they go to relatively high LEO, and also to avoid debris. There is a risk that they are hit by debris. That's why we developed the HET, that stands for Hall Effect Thruster. So it is an electric thruster which has a high ISP between 1000 and 1500. It has a low power consumption compared to other electric propulsion systems, and it is quite known in the space industry because it has been first flown by the USSR in 1971. More than 240 IGTs have been successfully fired in space. So what is the main principle of HET? You inject gas at the bottom of a channel, a circular channel, where you have a very strong radial magnetic field, and you emit electrons from a cathode. Those electrons will migrate to the anode because you have a relatively high voltage difference, about 500 volts, and when the electron enter the canal, they will begin to spin in it, to rotate in it because of the strong magnetic field. And those electrons will ionize the gas that you inject from the anode. And the fact that you have electrons that are migrating from the cathode to the anode will create a strong electric field that will accelerate the ions. Those ions are accelerated to 15 to 20 km per second, and they are then neutralized by the cathode that is emitting electron inside the plumb of the thruster. And to create the magnetic field, the usual solution is to use coils, and we insulate the channel from the coils via ceramic walls. And our innovation, in order to go to smaller thruster, is to use a fully ceramic design. They say that you replace the coils and the magnetic wall, the ceramic wall, by only magnetic ceramic. They say that you don't need complex and power-hungry coils anymore to create the strong radial magnetic field, and you don't need the ceramic wall anymore to insulate the channel from the thruster. And that leads to scalability towards very small thruster. And the one that you have here, the radiation parts that is in copper, is 2 centimeters wide. So that is a very small thruster that can be used on Cubesats. And we had here an illustration. So we have the thruster here. We have the cathode there, the big xenon tank, because we will use xenon, and 2 electronic cards. And I will explain what those parts are for. So the thruster unit, the thrusting unit, is composed of 3 main parts. So we have the electronic parts that deal with communication and health monitoring toward the OBC of the Cubesat, and the power management, because we need to create continuous 500 volts in order to power the cathode and the anode. We have all the gas managements with the tank and valves in order to have a micro debits from the tank to the thruster. The typical debit rate is 10 micrograms per second. And finally, we have the thruster plus the cathode that are the actual thing that are providing the thrust. So the main characteristic of our thrusting unit will be thrust between 100 and 150 micronewtons. It will be, we will have a range to choose because we can change, if we change the voltage between the anode and cathode, we can model the thrust, even though on traditional LTTs it is done by modulating the magnetic field. The power consumption will be quite low for electric thrusters, between 5 and 10 watts. When we count all the electronics, so for communication and health monitoring, but also for power generation. The ISP will be between 1000 and 1500 seconds, and the delta V, considering a mass of xenon between 30 grams and 150 grams, will be between 100 meter per second to 500 meter per second. And the weight will be less than 1 kilogram per proton, so it is suitable for use on the Cubesats. We want it to be a fully integrated unit, that is to say that it requires the minimum work for a team that want to use that kind of thruster to adapt it on their platform, and it will have a standard power input of 5 volts and 3.3 volts, and a standard data interface such as I2C or SPI to take the information from the OBC about when to thrust and to send health reports. And the size format will be less than 1 unit. And finally, we want it to be a very reliable solution. Let's say that we want to guarantee that the thruster will work at least after 5 years of the mission in order to deorbit it afterwards. And we want to qualify every of our components, especially the tank and the valve, with traditional safety standard in order to be able to launch a pressurized gas tank that is quite complicated for Cubesat. But we hope that if we have the traditional testing, we will be able to have that sample space. And we have one member of our team that is working inside a testing facility, so we have easy access to state-of-the-art testing facility. What are the performances of that unit? So to deorbit a 5 kilogram Cubesat, we will, in less than 400 days, from an altitude of 560 kilometers, that is to say the requirement for the deorbit device competition, we only need 35 grams of propellant. That's to say that we still have a lot of propellant left in order to accomplish other missions, because the minimum amounts that we will put inside the tank will be at least 100 grams, up to 500 grams. Therefore, we can accomplish new mission, and that is the main advantage to have a propulsion unit instead of only a desorbiting unit component. So we can perform debris avoidance in order to create new debris. We can also make orbit raising. What we thought is, for example, you are launched from the ISS, and then you want to go to a higher altitude in order to have to compensate the atmospheric drag, quite strong atmospheric drag. Therefore, you go from approximately 400 kilometer to 500, and then you can still desorbit your satellites with using only 70 grams of propellant for Cubesats. We also can do constellation deployments from one unique launch. Let's say that we can phase satellites on an orbital plane, and we can redeploy the constellation in case of a failure. And we can also think about displaced missions, because the delta V can be as high as 500 meters per second. So we want to increase the agility of a satellite, not to perform new missions, but still be able to desorbit afterwards. So, but if you had a propulsion unit on a Cubesat, you have to be able to know where you are going and where you want to put your satellite. And that's why we are developing orbitography services and software to know how to put your satellite where you want it to be. Therefore, we are currently studying mission design and mission control. They say to create the tools in order to compute where and when to thrust with your thrusting unit in order to perform the mission you want to perform, and also tools to deploy constellation from unit launch using only electric propulsion. And that is quite complicated because electric propulsion is only a very small thrust, so you cannot perform traditional maneuvers in order to make those kind of phasing. Finally, where we are now and where we are heading. So for now we have the thruster, we have the proof of concept that the thruster is working, and we are currently developing the subsystems, both the electronics and the tank and the valve. And we are also studying the orbital services. By the end of next year, we will have the first qualification model in order to be able to test the whole unit on the ground. And by the end of 2018, we hope to have the demonstration mission done. And the first sale and first use as a commercially available, or at least perfectly working unit in 2019. So, to conclude, we propose a solution to increase the agility of spacecraft in space, so we can reduce the risks to destroy our satellites by hitting a debris, and reducing the risk to create new debris. We can successfully deorbit a CubeSat even from a high altitude in a controlled way, and we can perform complex maneuvers that were impossible for CubeSats until now. Thank you.
Okay. Thank you for your presentation. So it's a time for question.
In your paper, you said that the cost estimate for this unit is 10 to 15% of the price of the satellite. So that can be a lot. That can be 200,000 euros just for the propulsion system. Is it realistic to be that high?
For our propulsion system, the first iteration will have to be less than 30,000 euros.
Less than 30,000 euros.
30.
30?
Yes.
30.
So it will be a very costly subsystem, but the problem that we have to space qualify it, we cannot afford to have a 50% failure rate on that kind of device. Therefore, we have to test it and we have to make it as reliable as possible. And so, yes, it will be a...
Yeah, you have to recover your development costs, but you cannot do that on the first unit you sell. You have to spread it out on all the units you plan to sell in the future.
Yes, but it's not only a 30,000 euro development.
Yeah, sure. So the price that you expect it to sell for is about 30,000 euros per unit.
It will be less than that.
Less than that.
Yeah, the upper limit is 25,000 euros.
Okay. Well, what is the expected thrust? I couldn't remember noticing it.
So it's 100 to 150 microns.
100 to 150, okay.
Yeah.
What's the pressure of the tank?
So the pressure of the tank will be around 70 bar. We want to qualify it to 100. Yes, it's a lot.
It's a lot, yes, for the
that's
cubes.
why we have to develop ourselves a tank in that will fit inside the CubeSat and that will withstand that kind of pressure. And it will, what we are heading now to do is to make a kind of carbon fiber tank in order to have it lightweight and withstand that kind of pressure.
One thing, you have the orbit plots. Can you go there?
Yeah. So
Here, where in the graph you fire?
sorry.
The variation is a bit
Yes.
different. But
Oh, why? Why they are different?
yes.
I have those in bigger. So basically, it's because it's a mass, different mass of cubes.
No, I mean it comes like this.
Oh, because so that is when your propellant is depleted. So we just go for...
Okay, first you have
Yeah,
controlled,
we trust only for like
Okay.
70 days.
then you have controlled, fast, and then, okay.
Yeah. So we can trust for 70 days and then the natural decay
Okay.
will be the rest.
Then it takes, you say, for 5 kilogram, more than 350 days. Okay. And I mean, another thing, your system weighs something like 1 kilogram, and it occupies 1 U.
So
Then you cannot deorbit at 1 U.
yeah, so it will be a little bit less than 1 U. So here you have 1 unit, but we expect to be able to raise the thrusting units because we still have some room left at the top in the teapot. And also we can make the tank smaller if we don't require it to be that huge. Because in that kind of tank, you can put 500 grams of cement, and for like just for dissipating, we can use a tenth of that. The tank can be smaller, but yes, it will be at least 2/3 of the units.
What was the fuel here? Is there no?
Do you already have a valve for the gas heat? You have a tank, you have a gas, but you need a valve.
Yes. So the valve we have. Well, there are a few manufacturers that do valves for vacuum chamber that can be adapted to Cubesats. However, there are still some work to do in order to reduce the size of the electronics of the valve and to reduce the size of the casing of the valve. But the main principle and the delta pressure and the debit that we want, it's already available on the shelf.
Okay. About your power, you said how much power do you need for operation?
Sorry?
How much power?
Oh,
Electrical power.
yes. So the electrical power is between 5 and 10 watts when you want to use it, and to have air support, it will be only 1 watt.
5 to 10 watt powers, the overall powers from the power supply.
Yes, there is no battery inside. There is no fail-safe.
Have you already demonstrated that numbers? Is it just estimate?
The 5 watt to 10 watts.
Yes.
So we know that the thrusting device is using 3 watts of power, and we expect the electronic parts not to use more than 2 to 5 watts.
How much efficiency do you assume for the power processing unit?
We are still assessing it because for the side power converter, there are some that are available with very high efficiencies. However, they might not deliver enough current.
Yeah.
At least for when you want to start the throttle, you have to have quite a high current. So we are looking for for different, for several opportunities, but the efficiency will be higher than 50%.
10 watt is almost maximum limit of about 3U Cubesat, right?
Yes, it's the limit. So the problem that what we were expecting that you don't use your payload while you were thrusting, because you just make like orbit raising or deorbitation, and you don't use your payload during that time. So you have power available for the
Okay.
So my question about ABCS. So, would you tell us the requirement for the actual determination control system?
Yes, so we will need quite a refined IOCS because yes, you have to be sure that you're thrusting where you want to thrust. However, we will be able to place the thruster next to the center of mass, behind the center of mass. So there should not be that many remaining couple. Cubesats, whenever you make quite an advanced Cubesat, but the one that will be using it 15 minutes, you will have a good AOC, yes. Yes.
You assume that the satellite will deorbit by thrusting for 70 days.
Yes.
But that assumes you're constantly thrusting, constantly using between 5 and 10 watts, constantly having ADCS perfectly pointing your thruster. I think it's a bit far-fetched. So you may thrust for an orbit and then switch it off, recover your batteries, everything, then fire for another orbit. So that means that your 70 days will increase a lot. You cannot do it in 70 days. That's absolute minimum.
So unfortunately we don't have time for questions. So after the session you can ask our speakers. So let's thank again our speaker.